so before we start, the midterm is on Friday, and Monday is when you guys get together to talk. Now, do you have plans to meet this evening? Have you discussed this with you there? No. You may want to get together and talk about various things, to review things. I will be here this evening if you need my assistance. I will be happy to apply. So, but I think you need to talk to you and figure out what you want to do. Okay.
Should we have another meeting?
Yeah, we should try and meet with you on Wednesday. Are you here Wednesdays? Nights?
Yes.
Yeah. We should try and meet with you on Wednesday, so we can study for our midterm tomorrow tonight, and then study for this midterm the rest of the week.
The other midterms are not so important, I think. This one is.
What's the meaning of minus order pound?
Minus order parameter.
Yeah. We have
Well, we've talked about that. But let's talk about it some more. So, when we have a molecule oriented somehow so that it makes angle theta with the z-axis, then T2, which is 1/2 3 cos squared theta minus 1, is going to be positive, right? So if the molecule is along the z-axis, this is 1, this is 2, this is 1, P is 1, right? So 1 means everybody's perfectly aligned, right? Then you make theta bigger and bigger. This number is going to get smaller and smaller. There comes a point where it's going to be 0, right? It's a special angle. People who do NMR call that the magic angle. I forget what it is, 57 point something. But there is a value when P2 goes to 0. That means when the angle is fairly large. And then when it goes to 90, then this guy is going to be minus 1/2. And it doesn't get smaller than that. So negative order parameter means that the molecules are not pointing this way, but they're kind of pointing perpendicular to the special direction. If all the molecules were exactly in this xy plane, then this would be exactly minus 1/2. Okay? So there's one special axis, and you can be either parallel to it when P2 is positive, or perpendicular to it when P2 is negative. So that's the difference. Okay?
Does that correspond to a second minimum of the free energy, like that?
Well, I mean, that in this curve that we drew, that looked like this, it corresponds to this.
Yeah, I mean, if you draw a plot like free energy versus S, then does that correspond to a higher minimum where the system is
I'm at a stable state.
metastable?
No. We'll do that right now. Let's draw a picture of the free energy as a function of S. Okay, so we have a self-consistent equation. In principle, we can solve it somehow. And then to figure out what's really going on, we need to look at the free energy that corresponds to those values of S. So 1/2 rho S squared minus 1/2 rho squared U S squared minus rho KT ln e to the rho U KT SP2 sine theta d theta. So that's okay. So once again, the values of S which you're liable to see in the lab are those which minimize this. You get the self-consistent equation, but you get more than one solution. Then to figure out which of those is likely to happen, you have to take that value, stick it back in here, and compare the free energy for two different solutions. So let's try to plot F as a function of S and see what we get. So now we do this f as a function of s. So here, you evaluate f as a function of s. These are constants, so these don't change. But the temperature can change. So we want to know how the free energy depends on s for different temperatures. And so at very high temperatures, it turns out that the free energy just looks like this. So pretty good approximation. But one thing that you want to note right away is that this is not an even function of s. If I replace s by minus s, this doesn't change, but this changes. So that means that whatever we draw here, the left and the right hand side will not typically be the same. Okay. So what happens next? So so this is a very high temperature. Now if you lower the temperature, this curve gets broader, and it's kind of hard to give a good, well, I don't know, you can imagine, sort of how this works. At a very high temperature, this denominator is big, so this number is small. So you can kind of do Taylor series expansion, it sort of works. And then the first term, again, vanishes. The second term, the first term would be linear in s, that vanishes because of the P2. The second term, the s squared term, will survive. And so there will be two terms with s squared. This guy and another s squared here that has temperature in it too. Right? And so I'm trying to argue for the sign here, but I'm not doing a good job. We'll see this more clearly later on. We'll actually do an expansion and you can see how these terms actually come about. It's not trivial because of the logarithm point. So let's not talk about how it comes about, but the essential feature is that it looks like this at high temperatures. If you lower the temperature, it looks like this. And then it turns out that a little kind of a bump develops on this side. If you lower the temperature more, then you find that you get an actual minimum here. So here, at some point, you will get first a point of inflection, which means that the slope is going to go to zero somewhere. And then you're going to get something that looks like this. I'm trying to make it maybe a little more faithful. So first thing that happens is here you get a point of inflection with zero slope, and then this guy will have a thing like this. And the point is that this bump, this point kind of splits into 2 points, okay? And if you keep going, then you get something that looks like, great job with this. So at some point, this minimum touches this line. Then after that, this guy goes negative. This maximum is shifting over here. And then there is a point where the slope is just zero. And then there's a point where we have a minimum here and a minimum there.
So then why doesn't it,
That looks pretty complicated.
so why doesn't it want to go to 0 always? I mean, before you get to some critical temperature.
So, okay, so the thing is that this is the free energy. To minimize the free energy, we set the derivative equal to 0. So solutions are points where the tangent is 0.
Right, so that point right there where S touches 0, that is the point where you're going to get your first isotropic, or that's where you get your first state that's going to have some non-zero S if you're lowering the temperature down. That point right there that you've drawn where it's touching 0, that is going to be, so if
No, it's going to be this, right?
So if we have this right here, and then this guy looks something like that, and this is T, and this is S, that's corresponding to that point right there, right?
Well, this corresponds to that.
But,
S is fine. When that happens when S is non-zero, it's finite. Right? So we have a point here, and it's a solution, but it's not a really good solution because this has lower free energy. Then we lower the temperature. That solution splits into two, this guy and this guy. And then this is a kind of a local minimum, so that's a metastable state, it's sort of okay. And this one is just unstable. Right? If you're up here, a little perturbation will lower the free energy, knock you either here or here. So the lower, so the higher S value, this is the higher S value, is metastable. This guy is unstable. And then the interesting thing happens when you come here. Now you have two solutions, this one, and they have the same free energy.
right, and
So-
that's right.
No.
There.
No,
No?
no.
But it's different.
Because I guess that's free energy.
Let me try to draw kind of a better picture maybe. So this is S, so this is, I'm drawing you a picture now. Looks like this. So this point here, I don't know, let's call this point here, corresponds to this point here, right? When you lower the temperature, a solution appears here. A zero slope point appears here, right? On these curves, it doesn't happen here, it becomes flat, and you have one point where it's slope is zero. So you have this guy, let's call this T star. Then, and of course, this is always a solution, that's a given, right? That's always here, the zero solution. Then you lower the temperature, the solution splits into two, a high value of S and a lower value of S. That's these points here. And this guy is metastable, this guy is unstable. Then you get to this point here, then at some point in between here, where the free energy of this guy and this guy is the same. And after that, when you cool below that, now the free energy of this guy, the non-zero S solution, is lower than the zero. So now, this is when you have the phase transition. This is where you jump from this point to this point. And that happens somewhere in here, that's T and I, that's a pneumatic isotropic transition. And then we keep cooling the system. And this point here corresponds to the point where this solution passes through zero. Right? Now that solution is this local maximum solution. Right? This keeps shifting over here. And there's a critical point, and after that, it moves over, it becomes just like that. This becomes a maximum, and this becomes a minimum here. So there's a critical temperature here when the curvature changes at 0 from upward to down. And that's Tc or T. This is T. No, I'm going to call this T dagger, I think. That's what I have in the notes. T dagger and T star. So there's a point where the curvature here changes from concave upward to concave downward. There's one point here where this guy is just flat. And that corresponds to T star. And after that, we get curved downwards, and we have another name here. Okay? So, now I put a picture like that in the notes. Hopefully it's legible. Okay, are we comfortable with this? Carl, you have a question?
Yes, I do.
Carl?
So when we have two minimas for negative and positive S, after we go down the T star, the one that corresponds to negative S, I mean the free energy minimum, is not as deep as the one that corresponds to.
That's right.
So does that mean that we cannot have a stable state with negative S?
Metastable.
Metastable. So that means if S is negative, this state is not stable.
Well, it's metastable. If you could get here somehow, it would be stable until you have a big enough fluctuation to knock you down there.
But 0 becomes unstable at that. The zero becomes unstable.
This becomes unstable, yeah. So the stability is kind of a nice story. So let's choose 3 colors: red, blue, and green.
Yellow. Yellow. Wait. Yellow. Choose yellow instead.
Yellow? All right.
And real quick, what about this, like maybe the second line up where it comes in and then it's just flat for a ways?
This one here.
Yeah.
That's a special point where the curvature here is exactly 0.
Right.
So it turns out that, you know, I think we'll talk about this later, that when you look at the quadratic term in the free energy, the S square curve, its coefficient changes sign. And that's really an important thing. So here it's positive, here it's negative. And when it vanishes, then you're at this particular point. So let's try to do this. So I'll put red. Red means unstable. Blue is stable. And yellow is metastable. Okay? Now let's label this guy here. First of all, at very high temperatures, what is the stable solution?
0.
0, right. So certainly up here, this is the stable solution. Okay. Now, after that, what happens? A new solution appears, and then we have 2 of those. What is this branch?
That's going to be metastable.
That's metastable, right. So this guy is metastable. Okay, what about the lower branch?
Unstable.
It's unstable, right. And this process continues all the way until we get to here, right? So this is red, and this is yellow. All right. Now, after this point, what happens? What is stable? This is stable, and this becomes metastable. So this becomes stable, and it's going to stay stable forever. And this branch, the 0 the zero solution becomes metastable. And this guy stays unstable. Because it's still a maximum. All right, and then what happens after that?
That becomes the negative becomes a metastable state.
Right, the negative becomes metastable.
And your zero becomes unstable.
Right.
I think you're missing one little piece of blue in between on the zero.
Ah, yes. Exactly, just so. Okay, that's it. Great. So, it's really interesting. So, there are three important temperatures. T dagger, where a new solution suddenly appears, and it's interesting that it doesn't appear down here. It appears at some finite value of S. So that's an interesting thing. Then T and I is the important one in a sense, because that's where the phase transition happens. That's when the pneumatic solution takes a lower free energy than the isotropic one. And then there's this T star, which is interesting because that's when the curvature of the zero solution changes, and the zero solution loses its stability and becomes unstable, and this negative solution becomes metastable. Now let me plot the free energy here, just to make it interesting. So we have these temperatures here, and the free energy of the zero solution is just zero, so that's easy to plot. And in fact, it stays zero. Maybe I should use in different colors for this, because we're not talking about stability, we're just talking about different solutions. All right, orange, green, what else? Brown. All right. So let's do the isotropic solution. Is this one here? Free energy zero. And I'll draw for you guys what this looks like. And it's kind of interesting. It looks, and I'm exaggerating what happens. We have something like a straight line that comes down here, and then we have another line. No. Sorry. No, I think that's fine. So yeah, that was fine. And the other one looks like this. So that's the story. So this guy is the isotropic, and this guy is the smaller s, and this guy is the larger s. We have, at each temperature, we have two values of s, the smaller one, this guy, and a larger one, which is that. And so your homework is, in fact, to plot this graph really precisely. So what you see happens then is this. You cool down the system, you only have one solution, you're happy, boom, another solution appears, but its free energy is higher, so we don't go there. Then that solution splits, you got two values of the free energy, it's still high. Then you get to this T and I, the pneumatic isotropic transition. There, the solution of this guy has the same free energy as the isotropic one. And after that, you're just going to go down here, because this is the lowest free energy. This guy and this guy both have higher energy. This is metastable, this is metastable.
So, does that mean we're gonna have particles jumping perpendicular to the axis and staying there until they overcome some energy barrier and then they pop out back to the...
Yeah, but very rarely. There's no real reason for it. I mean, they're sitting in this potential well pointing along the director, and yeah, maybe they'll go up here for a little while, but they're going to go back there because it's lower energy down there, so thermal fluctuation will not come back down. Well, it's interesting to do simulations of this, and then you can kind of see how it all works. But this is pretty much the whole landscape, and it's pretty interesting. I hope that you like it. What can I say? And so the point is that if you cool the system, you jump from zero order parameter to a large order parameter, and that's the first order phase transition. The discontinuous jump is a first order phase transition. In other systems, like magnetic system, this curve is symmetric, and the transition is second order, and we'll talk about that another time. But for now, the main thing is that just from having the free energy, the cycle system equation, we can really understand qualitatively at least what happens, and then in your homework, hopefully you'll be able to do these things with higher accuracy. Okay, quit here, and then we'll continue on Wednesday.